Hello class! So today, here in Statics of Rigid Bodies, we are now down to our 16th lesson, which is the centroid of composite figures. So for this lesson, students must be able to locate the centroid of composite figures, and students must be able to solve surface area and volume by theorems of Pappus. So let's start our discussion. So again, we will recall the centroids of some common geometric figures that we discussed from our previous recorded discussion. So here are the centroid of some common geometric figures such as rectangle, triangle, circle, semicircle, quarter circle, semicircular arc, and quarter circular arc. So be sure that you are familiarized with this established centroids, okay? Because we are going to use them in this discussion. So let's talk about now the centroids of composite figure. So when you say composite figure, it is a figure or shape that can be divided into more than one of the basic figures such as rectangle, triangle, circle, semicircle, quarter circle. So if the given area can be divided into parts, each centroid of which is known. So we know that rectangles, triangles, semicircle, quarter circle, semicircle, their centroids are already known or established, right? So the moment of the total area will be the sum of the moments of area of each part. So we apply the Barignon's theorem, no, for that concept. So the centroid of the composite figure is determined by applying the following equation. So these are ax bar is equal to summation of ax and ay bar is equal to summation of ay, wherein the capital letter A here is the total area of the composite figure. So to solve for that, you just have to solve the area, okay, of all the composite shapes, okay, that compose the figure, and you just have to sum them up. Okay, and then x bar and y bar here, these are the x and y coordinate, okay, of the centroid of the composite figure. So these are the unknowns that we are solving here. So that will be equal to summation of ax and summation of ay. So the small letter a here, these are the area of each shape that compose the composite figure. Okay, and then x and y here, these are the x and y coordinate of the centroid of each area, of each shape, no, with respect to the reference point. So x, it will be measured horizontally, no, from the reference point, and y, that will be measured from vertically from the reference point. Okay, so similarly, we can also use this, no, this concept for lines. So these formulas, okay, so these are applicable for areas, no, for composite areas, but also we can apply this, no, for composite lines. Okay, so a similar process may be applied to lines. The given line may be divided into finite segments whose centroids are known, and the following equations may be used. So these are Lx bar is equal to summation of Lx, and then Ly bar is equal to summation of Ly. Wherein capital letter L here, okay, this is the total length, okay, total length of the composite lines. Okay, x bar and y bar, these are the coordinates of the centroid of that composite lines. Okay, so small letter L here. Okay, these are the lines that compose, no, that compose the composite line. So we will multiply that to x and y, wherein x and y here are the x and y coordinate of the centroid of each line, no, that compose the composite figure. Also take note here that the sign of the moment arm of the area should follow the sign convention depending on its position with respect to x or y axis. Okay, so uh, 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 take note that the sign for this x and y coordinate, it depends on its position. So if the point, no, or the centroid, okay, it's located at the right x-axis, okay, so that x coordinate, it will be positive. But if it's at the left, no, if it's the left, no, at the left x-axis, no, if it's at the left with respect to the reference point, that will be negative. And for y coordinate, if it's above, no, the reference point, no, if it's at the upper y-axis, no, so that will be positive. But if it's at the lower part of the y-axis, no, if it's below, no, the reference point, no, so that y coordinate will be negative. Okay, so you have to you have to consider that, no, in our computation, because that will be important. If the sign that you use is wrong, okay, so it will give you a wrong answer. Okay, so you have to be careful with that. Okay, so let's start solving sample problems. For sample problem number 1, a slender homogeneous wire of uniform cross-section is bent into the shape shown in the figure. Determine the coordinates of the centroid. So as we can see here in this problem, no, so this is a slender homogeneous wire. Okay, so this is the slender homogeneous wire that we are mentioning here. Okay, so this is this composite line, no? This is in blue ink. No, so we are just considering a composite line here, okay? So this is not a composite area. So this is a composite line that is composed of this line, this 6 inches line, okay, and also this semicircular arc, no? So this is a semicircular arc, and then we have here an inclined line, okay, which is 8 inches. So for the semicircular arc, this is 4 inches in radius, no? So we are going to solve the coordinates of the centroid, okay, of this composite line, no? So let's start solving this. Okay, so for this problem, we are going to solve the coordinates of the centroid, no, of this composite line. Okay, so to solve this, we are going to divide this composite line, no, into its component parts. So its component parts are the 6 inches line, okay, this 4 inches radius semicircular arc, okay, and we have here an 8 inches inclined line. Okay, so this is 30 degrees from the horizontal. So we are going to solve for the length of each line, no, and also for the x and y coordinate, no, of each line, no, with respect to the reference point. So our reference axes here are this y-axis and x-axis. So the reference point will be here. No, so we will measure the x and y coordinate from this reference point. Okay, so for the length of the first line, which is 6 inches, so that is already 6 inches. For the length of this semicircular arc, so its formula is pi r. So basically, it's just the circumference, no, of the semicircle. No, for a circle, its circumference is 2 pi r, right? So since this is a semicircular arc, so that will just be the half of that, so that will be pi r. So our radius here is 4, so therefore the length of this semicircular arc, okay, that is 4 pi. Okay, for the 8 inches inclined line, so its length will be 8 inches. Okay, now for the x coordinate, okay, of the centroid of each line. So for this line, okay, its centroid is at the center. No, is at the center of this line, which is here. No, so the x coordinate will be the distance horizontally from the origin. Okay, so the distance, this distance, okay, this distance from the origin of this 6 inches line, okay, this is 4, right? Since this will be that distance. Okay, so this is the radius of this semicircular arc, right? This is also the radius, right? So this is 4 inches. So therefore, the x-coordinate of this line, okay, from the reference point, okay, that is 4 inches. Okay, so since it is at the left, no, it is at the left of the reference point, no, it is at the left x-axis, no, therefore, the x-coordinate will be negative. Okay, and also for the semicircular arc, no, its x-coordinate. Okay, so we know that the centroid, no, of this semicircular arc, no, it will be somewhere here. Okay, so its distance horizontally from the origin or from the reference point, that is 0, right? Because it is at the origin, no? So our x-coordinate for the semicircular arc will be 0. So this will be 0 here. Okay, now for the inclined line, no, this 8 inches inclined line, its centroid, no, is at the center of this line. Okay, so if this is 8 inches, so the center will be 4 inches, no? This distance will be 4 inches, right? So we are going to solve for the x-coordinate. So that will be the horizontal distance of this point, no, from the reference point, no? So this distance will just be 4, no, 4 plus this distance. Okay, so this distance will be the adjacent side of this triangle that will be formed here. Okay, so this triangle, its angle will be 30 degrees and its hypotenuse will be 4, no? 4 inches. So we are going to solve for this adjacent side, no, to solve for the x-coordinate that we need here. Okay, so the adjacent side, to solve that, no, we will use cosine. Cosine 30 degrees, that is adjacent over hypotenuse, right? So to solve for the adjacent side, that will just be hypotenuse, which is 4, times cosine 30. So this will be that value, no? So the x-coordinate of the centroid of this line will just be 4 plus 4 cosine 30 degrees. Okay, so the value for that will be 7.46410. Okay, so this will now be the x-coordinate, no, of this component parts, no, of the composite line. Okay, so for the y-coordinate, so for this 6 inches line, no, so again, its centroid is at the center, no, of this line, which is here. So the distance or the y-coordinate, okay, of this line, okay, so that will be the distance, no, that is measured vertically from the reference point. So that will be 3, no? So that will be 3, and since it is at the upper part of the y-axis, or it is above the reference point, so that will be positive. Okay, now for the semicircular arc, no? So for the semicircular arc, again, we know that its centroid will be somewhere here. Okay, so its y-coordinate, or the measure of its distance vertically, no, of the centroid, no, from the reference point, no, that will be 2r over pi, no? So this is already an established, this is already an established centroid. Okay, so our radius here is 4, so that will just be 2 times 4 over pi. So that will be 8 over pi. No? So its y-coordinate, no, from the reference point, that will be 8 over pi. Now for the inclined line, no, so what we need here is the y-coordinate, no? So the centroid of this inclined line is somewhere here, no? So this is at the center, no, of this 8 inches line, no? So this will be 4 from here, no? So again, what we need here is this distance, no? So we need to measure the distance of the centroid of this inclined line, no, from the reference point vertically. Okay, so it's this distance will be the opposite side. Okay, will be the opposite side of the triangle formed here, no? So we have here the hypotenuse, which is 4 inches, and then the opposite side, and then the angle here is 30 degrees. So we can use sine 30 degrees here, and that will be equal to opposite side over hypotenuse. So to solve for that opposite side, that will just be hypotenuse times sine 30. So the hypotenuse for this will be 4 inches. No, so that will be 4 sine 30 degrees. That will be 2 inches. So this will now be the values of the length and the x and y coordinate of each line here. Okay, and we are going to use our formula here. So for our formula to solve for x bar, which is the x coordinate of the composite line, or this composite figure, no? So for L, for the capital letter L here, so we just have to solve for the total length. So we just sum this up, 6 plus 4 pi plus 8, and the answer for this will be 26.56637. Okay, and then for L and X here, small letter L and X here, we will just sum up length L and then times -4. Okay, so again, our total length here is 26.56637. 2.56637 x bar, that will be equal to the summation of all the length, no, of the of each line times its respective x coordinate, no. So that will be 6 times -4, okay, plus 4 pi times 0 plus 8 times 7.46410. No, so here we can now solve for x bar. So solving for x bar, that will just be 1.34429 inches. So don't forget to include the unit, ha. Okay, so for our x bar, this will now be the answer. Now, to solve for ly bar, that will just be equal to 26.56637 y bar, and that will be equal to the summation of the length of each line times its respective y coordinate. So that will just be 6 times 3 plus 4 pi times 8 over pi plus 8 times 2. Okay, so solving for y bar, so we will just divide both sides by the total length. So to solve for y bar, that will just be 2.48434 inches. So again, don't forget to include the unit. So the unit for this is inches. So this will now be the coordinates of the centroid of this composite figure. Okay, x bar and y bar. So this will now be the answers. Now, for sample problem number 2, determine the centroid of the shaded area shown. So we are now dealing here with a composite area. So this composite area, we can divide this into basic shapes, right? So we can divide this into this rectangle. Okay, we can divide this into this rectangle and this semicircle. No, so this composite figure is composed of 3 geometric shapes, and each geometric shape, okay, their centroids are known, right? So we can solve this, no. So let's solve the centroid of this composite area. Okay, so to solve for the centroid of this composite area, we are going to divide this composite area into its component areas. Okay, so we are going to construct a table here, okay, wherein we will show here the geometric figures, no, that compose the composite figure. So these are rectangles, triangle, okay, and semicircle. So for the rectangle, okay, its base is 4 feet and its height is 3 feet. Now, for the triangle, okay, so this side, okay, so this is also 4 feet, okay, and this side, so since the radius of the semicircle is 2 feet, okay, so this side will just be 2 plus 2. No, so this will be 4 feet. And for the semicircle, so its radius is 2 feet. Now, we are going to solve for the area of each geometric shape, no? So for rectangle, we know that its area is just base times height, so that will just be 3 times 4, and that will be 12. Now for triangle, its area will just be 1/2 base times height, so that will be 1/2 times 4 times 4, so that will be 8. And then for semicircle, so its area is just half the area of a circle. So the area of a circle is pi r squared. So half of that will be 1/2 pi r squared, wherein our radius here, okay, so that is 2 feet. So that will be 1/2 pi times 2 squared. So the area will be 2 pi. Okay, now we are going to solve for the x-coordinate of the centroid of each shape. Now for the rectangle, okay, so we are going to solve for its x-coordinate. So our rectangle is here. Okay, so our reference axis, okay, is here. No, this is the y-axis, the reference y-axis, and this is the reference x-axis. So our reference point will be here. Okay, so our x and y coordinate will be measured from this point. Okay, so for the x-coordinate, no, of the centroid of the rectangle, so this is the rectangle. So its centroid is at the center, right? So here at the center. No, so the x-coordinate, no, of this rectangle, no, will be this distance. This will be the horizontal distance from the origin, from the reference point. So this distance is 2 feet. No, so this is 2 feet. So this is at the right side of the reference point. Therefore, it will be positive. Okay, now for the for the x coordinate, no, of the centroid of the triangle. So this is the triangle, no. So its centroid, as we know, is at this point, no. So its coordinate, no, from here, from the reference point, will be 2/3, okay, of this of this length of the triangle. So this is 4 feet, so this will just be 2/3 of this side, okay, which is 2/3 times 4, so that will be 8/3. Now for the semi circle, no, so its centroid, no, as we know, it will be somewhere here at this point, no. So its horizontal distance from the reference point, that will be the x coordinate, so that will just be 4, no, 4 plus this distance. So this distance, no, from the established centroid of semicircle, this is 4r over 3 pi, right? So this is 4r over 3 pi. Okay, so that will be 4 plus 4r over 3 pi. So our radius here will be 2 feet. Okay, so this will now be 4 plus 4 times 2 over 3 pi. So this will be 4.84883. So that will be the x-coordinate of the centroid, okay, of the semicircle. Now, for the y-coordinate, okay, so for the y-coordinate of the centroid of the rectangle, so this will be the vertical distance, no, from the origin. Okay, so this will be half of 3 feet, which is 1.5 or 3 halves. Okay, so that will be the y-coordinate of the rectangle. Now, for the triangle, the y-coordinate of its centroid will be 3 feet plus this distance. So this distance is 1/3, no, 1/3 of this side. So this side is 4 feet, so that will be 1/3 of 4, no. So the y-coordinate of the triangle, no, from the reference point, that will be 3 plus 1/3 of 4, no. So that will be 13/3. Now for the y-coordinate of the semicircle, okay, so its y-coordinate will be 4 plus the radius, right? So again, the centroid of this semicircle is at this point. So the y-coordinate of that point, no, will be 4 plus the radius, no, which is 2. So that will be 3 plus 2. So its y-coordinate will be 5. Okay, so here we are going to use our formula to solve for x bar and y bar, which are the coordinates of the centroid of this composite figure. So for the total area, we will just sum up 12, 8, and 2 pi. So this will be 26.28319. Okay, so that will be the total area. Now for the x bar, that is unknown, and then summation of all the area times its respective x coordinate. So this will be 12 times 2 plus 8 times 8/3 plus 2 pi times 4.84883. Okay, so solving for x bar, we will just divide both sides by the total area. No, so this will be 2.88395. So again, don't forget to include the unit. So the unit for this is feet. So you can already box that. Now for y bar, so the formula is ay bar is equal to summation of ay. So the total area again is 26.28319 times y bar, that is the unknown, and then multiplied by the area, no, times the respective y coordinate. So that will be 12 times 3 halves plus 8 times 13/3, then plus 2 pi times 5. No, so solving for y bar, we will just divide both sides by the total area. So the answer for this will be 3.19910 feet. No? So this will now be the answers for this problem. The x bar is 2.88395 feet, and the y bar is 3.19910 feet. So this will now be the answers. Now for sample problem number 3, the dimensions of the T-section of a cast iron beam are shown in the figure. How far is the centroid of the area above the base? Okay, so we are going to solve for the centroid of this composite area, no, from the base. So the base is here. So we are going to solve, no, for the y-coordinate, no, of the centroid of this composite area. No, so let's try to solve this. So again, we are going to solve the distance of the centroid of the area from the base. So we are going to solve for y bar. So our reference axis here will be at the base. No, so we are going to solve for the y bar. Now, to solve that, no, we are going to divide this composite area into its component areas. No, so we will divide this into these two rectangles. Okay, so for the first rectangle, its dimensions will be base is 1 and then its height will be 8 inches. Now for the lower rectangle here, okay, so its base is 6 inches, okay, and its height will be 1 inch. Okay, so we are going to solve for their respective area and y coordinate. So for the area of the first rectangle, no, its area will just be 1 times 8. So that will be 8. No, and the area of the second rectangle, that will just be 1 times 6. So that will be 6. Now for the y coordinate, no, for this rectangle, no, so the centroid of this rectangle will be at the center. Okay, so this point, no, its y coordinate, no, will be this distance, no, from the reference axis, which is at the base. So this will be 4 plus 1. Okay, so that will be 4 plus half of 8. So half of 8 is 4. Okay, so that will be 5. Okay, now for the this rectangle, okay, so its y coordinate from the base, no, it will just be 1/2. No, so that will be 1/2. So solving for the total area, that will be 8 plus 6, so that will be 14. So applying our formula, ay bar is equal to summation of ay. Okay, so our total area is 14 times y bar, and then equal to the summation of all the areas times its equivalent y coordinate. So that will be 8 plus 5, and then 8 times 5 rather, and then 6 times 1/2. Okay, so class, don't forget here the ano ha, to consider the sign, no, for the coordinates, no. So in here, it just so happened that our y coordinates here are above the reference axis, so this will be positive. Okay, so this will be positive and this will also be positive, no, but don't forget to consider that, okay, in our other problems. Okay, so solving for y bar here, so we will just divide both sides by the total area. So y bar will just be 3.07143 inches. Okay, so this will now be the answer for this, no. So you can check, no, if your answer is logical. So our y bar is 3.07143. So approximately, if this is 1 inches, 1 inches, 1 inches, so it will be somewhere here. No, the centroid, no, of this the centroid of this composite area is somewhere here. Okay, so meaning to say, no, from this point, no, if we pass through a axis here or an axis here, okay, so the area above should be equal the area below. Okay, so here, if we are going to absorb this, no, or analyze this, no, we can say that if the centroid is at this axis, no, so the area above is actually approximately equal, no, that is actually equal, no, that is actually equal to the area below, no. So our answer, no, can be ano naman, can be logical, right? So we can say that this is ano naman, correct, no, based on our analysis by observation. Now, for sample problem number 4, locate the centroid of the shaded area shown in the figure. So this is the composite area that we are going to analyze. No? So we are going to solve for its centroid. So we can actually divide this composite area into 3 triangles, right? This first triangle, this second triangle, and this third triangle. No? So let's solve this. Okay, so to solve for the centroid of this composite area, we're going to construct a table here. Okay, so we will divide this into its component area, no, into component geometric shapes. So the first component area here will be this triangle. Okay, so this triangle, its dimension will be, this will be 6 inches. So since this is 6 inches here, so this will also be 6 inches. And then since this is 6 inches here, so this side will also be 6 inches. So this will be the dimensions of each side, 6 inches and 6 inches. Now for the second triangle, so this will be the second triangle, this will be the second component area. Okay, so this triangle, its dimension also, this is also 6 inches, this is also 6 inches. So this will be the dimensions.
okay, of this triangle. Okay, and also for the third triangle, so this will be the third triangle. So its dimension for this side, so this will just be 6 plus 6, so that will be 12. And then this side will just be 12 minus 6, no? So this will be 6 inches. So this will be the dimensions of the side of this triangle. Now we are going to solve for the area of each component figure here, and then solve for their x and y coordinate with respect to the reference point. So in this case, our reference point will be at this point. So our x-axis is here and our y-axis is here. So our reference point will be here. So the x and y coordinate will be measured from here. No? Okay, now for the area of the first triangle, so this will just be 1/2 base times height. That will be 1/2 times 6 times 6, so that will be 18. Also for this triangle, so this will just be the same, 1/2 times 6 times 6, so that will also be 18. Now for this triangle, this is 1/2 6 times 12. No, so this will be 36. Now for the x-coordinate, also for this triangle, okay, so its centroid will be somewhere here, right? So it will be somewhere here. So its x-coordinate, so this will be that distance, the x-coordinate. So the x-coordinate for this will be 1/3, no, of this side, which is 6, no? So this will be 1/3 of 6, no? So that will be 2. Now for the x-coordinate of this triangle, no, the x-coordinate of this triangle, the centroid of this will be somewhere here. So its x-coordinate, no, its x-coordinate will be this distance, no. So this distance will just be 6 plus this side, no. So this distance is actually 2/3, no. So this is 2/3 of 6, right? So this is 2/3 of 6. Okay, so this will be 2/3 of 6 plus 6. So that will be the x-coordinate. So that will be 10, right? 6 plus 2/3 ng 6, that will be 10. Okay, now, for the third triangle, so this is the third triangle. So its x-coordinate, no, its centroid will be somewhere here, right? So its x-coordinate will be this distance. So this distance is actually 1/3 of this of this distance, which is 12. So 1/3 of 12, so that will be 4, no? So that is the x-coordinate. So again, all the x-coordinates, no, they are all at the right side, okay, of the reference point. So they will all be positive. Okay, so don't forget to consider that, okay? So it just so happened here that all the x-coordinates are positive, okay? Or at the right side, so they are all positive. Now for the y-coordinate, no, for the first triangle, its y-coordinate, okay, so its y-coordinate will be this distance, no, the coordinate of its centroid. So this distance is actually 2/3, no, 2/3 of this distance, which is 6. So 2/3 of 6, that will be 4. Okay, now for this triangle, its y-coordinate, or the y-coordinates of its centroid, will be this distance. So this will also be 2/3 of 6, no? So that will be 2/3 of 6, that will be equal to 4. Now for this triangle, its y-coordinate, okay, its centroid is here, so the y-coordinate will be 6 plus this side. Okay, so this length, no, or distance will be 1/3, no, of 6. So this will be 1/3 of 6 plus 6. Okay, so the answer for this, 6 plus 1/3, 6, that will be 8. So this will now be the y-coordinate. So all the y-coordinates here are above the reference point. So they will all be positive. Okay, so applying our formula to solve for x bar and y bar, so the total area, okay, we have to sum up all the areas here. So this will just be 18 plus 18 plus 36, so that will be 72. Okay, so applying that to our formula, so this will be 72 x bar, so that will be equal to summation of ax. So our a, okay, are these areas, and then x will be the corresponding x coordinate, no? So this will be 18 times 2 plus 18 times 10 plus 36 times 4. Okay, so solving for x bar, we just divide both sides by the total area. So this will be 5 inches. Again, don't forget to include the unit. So the unit for this is inches. So the x bar is 5 inches. Now for y bar, so applying the formula, ay bar is equal to summation of ay. So our total area is 72. And then y bar is equal to 18 times 4. So this will be 18 times 4 plus 18 times 4 also plus 36 times 8. Okay, so solving for y bar, that will just be 6 inches. So this will now be the answer for this problem. No? So the coordinates of the centroid is this x bar and y bar. So we can check no if these answers are logical. So basically, if the x coordinate is 5 inches, so 5 inches, and then the y coordinate is 6 inches. So our answer no is somewhere here at this point. 5 inches, 6 inches, so it will be somewhere here at this point. So if you're going to analyze, no, if the area above is equal to area below, so approximately they are equal naman, no, based on our observation. And also the area at the left and the area at the right, no, so by observation, we can say that it can be equal naman. No? So we can say from here, no, that our answers are logical. Okay, so let's proceed now to sample problem number 5. Find the coordinates of the centroid of the shaded area shown in the figure. Okay, so this is the composite area here. Okay, so as we can see here, we can see a semicircle here, no? Also a quarter circle here, and a triangle here. But the problem here is that these shapes, okay, these shapes are actually not part of the shaded area, right? So what we're going to do here, okay, what we're going to do here is consider the entire rectangle. So this is the entire rectangle, right? So this is the entire rectangle. And what we're going to do here is subtract, no? Subtract this semicircle, this quarter circle, and this triangle, okay, to solve for this composite area, right? So again, I will repeat that. Okay, if we have this rectangle, so this rectangle, its dimension will be 12. Okay, so this will be 12 plus this side. So this side is 6, no? So this is 12 plus 6, so that will be 18. So that will be the dimension of the rectangle, 12 by 18. Okay, so if we are going to subtract the area of this semicircle, of this quarter circle, okay, and this triangle, we can get this composite area, this shaded area. Okay, so that's what we are going to do here, no, to solve for the centroid of this shaded area. Okay, so we are going to solve the coordinates of the centroid of the shaded area. So again, no, so to solve this, we are going to construct a table, and we will divide, no, this composite figure into its composite area. So in this case, we are going to draw here the rectangle. No, so the rectangle, its dimension will be 18 and then 12. Okay, so from this rectangle, we are going to subtract. No, we are going to subtract this semicircle. Okay, we are going also to subtract this quarter circle. Okay, and we are going also to subtract this triangle. Okay, so the area of the rectangle, that will be 12 times 18, so that will be 216. The area of the semicircle, okay, so this will be negative, ha? Okay, since we will subtract this area from the area of this rectangle. Okay, so the area of this will be negative 1/2 pi r squared. So this will be negative 8 pi. Now, for this quarter circle, no, so its area will be 1/4 pi r squared. So we will make it negative because we will subtract this also from this rectangle. So its area will be negative 9 pi. No, also for this triangle, no, so for this triangle, so the dimension of this triangle, no, since this is 12 and this is 6, no, therefore this side will be 6. And this side is actually equal to this side. So if this is 6 inches, so this will also be 6 inches. So that is the dimension, okay, of the triangle. So the area of the triangle will be 1/2 times 6 times 6. So the negative here indicates that we will subtract no, this area, no, from this rectangle, from this shaded area. Okay, so this will now be the areas. Now we can ano, no, solve for the total area. So solving for the total area, this will be 216 minus 8 pi minus 9 pi minus 18. So the answer will be 144.5929 Okay, now for the x coordinate, so we will solve the x coordinate of each area. So for the rectangle, no, so our x and y coordinates will be measured from the reference point. So our reference axes are here. So the y-axis is this axis and the x-axis is here. So the reference point will be here at this point. So the x coordinate will be measured horizontally from the reference point. So the x-coordinate of the centroid of the rectangle will be at the center. So its x-coordinate will be half of 18. So that will be 9. And then for the semicircle, okay, so its x-coordinate, okay, so the centroid of this semicircle will be somewhere here at this point. No? So its x-coordinate will just be the radius, which is 4. Okay, so that will be positive since it's at the right, no? It's at the right of the reference point, no? So that will be positive. Now for the quarter circle, so this is the quarter circle. So its x-coordinate, so the the centroid, no, of this quarter circle, okay, will be somewhere here, no, at this point. So this point, no, it can be measured from here. So this is 4r over 3 pi. So the measure of 4r over 3 pi is here, from here, not from here. Okay, so the measure of the x coordinate will be 4r over 3 pi. So this 4r over 3 pi or this point, no, from the reference point, it will just be 18. So this will be 18 minus 4r over 3 pi to solve for this distance. So this is the x coordinate that we need. Okay, so again, that is 18 minus 4r over 3 pi. No, so that will be 15.45352. Now for the triangle, no, for this triangle, its centroid will be somewhere here. No, so its x coordinate now will be this distance, which is 2/3, no, 2/3 of 6. So this is 2/3 of 6 plus 12. Right? So that will be the x coordinate from the reference point, no, of the centroid of this triangle. Okay, so again, that is 12 plus 2/3 of 6. So that will be 16. So that will be positive since it's at the right side of the reference point. Now for the y coordinate, for the rectangle, its y coordinate will be here. No, so this will be 6. This is half of 12. Right? So this will be 6. Now for the semicircle, okay, so the centroid is here. So the y-coordinate will be this distance. So this distance, no, so for this for this semicircle, we know that this distance is 4r over 3 pi. Right? So the 4r over 3 pi is from here, not here. So the y-coordinate of this semicircle or the centroid of this semicircle will just be 12 minus 4r over 3 pi. So that we can solve for this distance. So that will be 12 minus 4r over 3 pi. Our radius here is 6, Okay, so 4 pala rather, 4. We are considering the semicircle. Okay, so this will be 12 minus 4 times 4 over 3 pi. So that will be 10.30235. Now for the quarter circle, so this is the quarter circle. So the y-coordinate of its centroid, so this is the centroid. So this distance, this distance will just be 12, no? So 12 minus 4r over 3 pi. So this is the 4r over 3 pi, Okay, so our radius here is 6. So the answer for this will be 9.45352. So this will now be the y-coordinate of quarter circle. Now for the triangle, so it's the y-coordinate of its centroid will be this distance. So this is 1/3, no, of this side, which is 6. So this is 1/3 of 6. So that will be 2. Okay, so again, all the coordinates here are positive since they are located at the right and they are located above, no, the reference point. So solving for the total area here, so we already have this, no? So let's solve the coordinates here by using our formula. So AX bar is equal to summation of AX. So our total area is 144.59292. Okay, times X bar, that will be equal to A times X. So we will multiply the area and the corresponding X coordinate. So that will be 216 times 9 minus, since this is negative here, minus 8 pi times 4 minus 9 pi times 15.45352 minus 18 times 16. So solving for x bar, we will just divide both sides by 144.59. So the answer for x bar will be 7.73572 inches. So again, don't forget to include the unit. Now, to solve for y bar, so that will just be ay bar is equal to summation of ay. So that will be 144.59292 y bar. So that will be equal to a times its corresponding y bar. So that will be 216 times 6. And then minus, since this is negative, minus 8 pi times 10.30235 minus 9 pi times 9.45352 minus 18 times 2. So solving for y bar, that will be 5.07481 inches. So again, we can check, okay, our answer if it's logical. So basically, if the x bar is 7.73, so since this is 18, no, 18, so we can assume that it's somewhere here. And then the y bar is 5.07, so we can assume that our answer is somewhere here at this point, right? 5, so half of 6. So approximately here at this point, no? So we can say from our answer that the area above, okay, if we will have our axis here at the centroid, no, so the area above is equal to the area below, and the area at the right is also equal to the area at the left, no? So we can say that our answers are logical naman. Okay, so for sample problem number 6, locate the centroid of the shaded area in the figure created by cutting a semicircle of diameter r from a quarter circle of radius r. Okay, so this is the shaded area. Okay, so to solve for this shaded area, we will just subtract the area of this semicircle, okay, from the area of this quarter circle. Right? So this quarter circle, its radius is radius r. Okay, and for this semicircle, if this is r, so therefore the radius of this semicircle is r over 2. Okay, so let's solve this. Let's solve the centroid, no, of the shaded area. Okay, so to solve this, we are going to construct a table here. Okay, so we are going to consider the quarter circle. Okay, so the quarter circle. And then this semicircle, we are going to subtract this semicircle from the quarter circle. So for the area of the quarter circle, no, so that will just be 1/4 pi r squared. So our radius here is r, no, so this will now be the area. Okay, so for the area of the semicircle, so this will just be 1/2 pi r squared. No, so our radius here, the radius for this semicircle, no, if this is r, so the diameter is r, no, so therefore its radius is r over 2. So its radius is r over 2, so this will be 1/2 pi r over 2 squared. No, so this will be negative just to indicate that we will subtract this area from this area. Okay, so solving for the total area, that will just be 1/4 pi r squared minus 1/8 pi r squared. So that will be 1/8 pi r squared. Now for the x-coordinate, of this quarter circle, so its centroid will be somewhere here, no, of the quarter circle. It will be somewhere here. So its x-coordinate will be this distance. So this is 4r over 3 pi. Okay, so our radius is already r, so that will now be the x-coordinate. Now for the semicircle, so this is the semicircle. So its centroid will be somewhere here. Okay, so its x-coordinate, will be 4r over 3 pi. So in this case, the radius here is r over 2. So 4r over 3 pi, so this will be 4 times r over 2 over 3 pi, so that will be 2r over 3 pi. So that will now be the x-coordinate. So they are both positive, okay, since these coordinates are located at the right of the reference point, so they will be positive. Now for the y-coordinate, for the quarter circle, so the y-coordinate of its centroid will be this distance. So this distance is also 4r over 3 pi. Okay, now for the semicircle, so its centroid is here, so its y-coordinate will be this distance. So this distance is the radius of the semicircle. So the radius of the semicircle is r over 2. So applying our formula here, so to solve for x bar, that will be ax bar is equal to summation of ax. Our total area is 1/8 pi r squared. And then times x bar, that will be equal to a times x. So area times its corresponding x coordinate. So that will be 1/4 pi r squared times 4r over 3 pi. And then minus, since this is negative here, minus 1/8 pi r squared times 2r over 3 pi. So solving for x bar, so we will simplify this first, no? So here, we can cancel pi, okay? And then this will become, 4 will also be canceled, no? So what will remain here is 1/3 pi, pi will be canceled also. So what will remain here is 1/3 r cubed, no? So this will become r squared times r, so that will be r cubed. And also for this, we can cancel also the pi, okay? And we can multiply this, not 1 time, so that will be 2 over 8 times 3, so that will be 24. So 2 over 24, if we reduce that, that will be 1 over 12. And then we have here r squared times r, so that will be r cubed. So we can combine this further, no, since they are both r cubed. So 1/3 r cubed minus 1 over 12 r cubed. So that will be 1/4 r cubed. Now to solve for x bar, we will divide both sides by 1/8 pi r squared, no? So this will be multiplied both sides by 8 over pi r squared, no? So this will be canceled. Okay, so this will be canceled, and then x bar will be 2r over pi. Okay, so this will be equivalent to 0.63662r. So this will now be the answer for x bar. So this is 0.63662r. Okay, now for y bar, so we will use our formula. Again, the total area is 1/8 pi r squared. Okay, and ay will be a times the corresponding y coordinate. So that will be 1/4 pi r squared times 4r over 3 pi minus, since this is negative here, 1/8 pi r squared times r over 2. No, so solving for this first, no? So pi will be cancelled here. Okay, 4 will be also cancelled. So what will remain here is 1/3 pi r cubed. Here, this will become 1 over 8 times 2, no? So that will be 1 over 16 times pi times r squared times r. So that will be r cubed, no? So combining this, no? So this will be 1/3 r cubed minus 1 over 16 pi r cubed. So if we combine them, so this will be 0.13698 r cubed, no? So solving for y bar, we will divide both sides by the total area. Okay, so solving for y bar, this will just be 0.34882 r. So this will now be the answer for y bar. So this will now be the answers for x bar and y bar. Okay, for sample problem number 7, locate the centroid of the shaded area in the figure. So this is the shaded area. So we are going to analyze this, okay, to solve for its centroid. Okay, so this is the given composite area. Okay, so if you are going to solve for its centroid, we have to decompose this, no? We have to divide this into its component areas. Okay, so in this case, this is a little bit complicated, right, to divide this, no? So we are going to analyze this, no? So as you can see here, no? So this rectangle, right? You can see this rectangle, right? So this is 6 centimeter and 9 centimeter. If we solve for its area, okay, of this rectangle. Also, for the area of this quarter circle, and also for the area of this rectangle also. So this rectangle is 4 centimeter, and this is 5 centimeter, right? So this is the dimension, that is the dimension of this rectangle. So again, if we solve for the area of this rectangle, of this quarter circle, and this rectangle, we can solve for this total area, right? So this will be the total area. Now, to solve for the shaded region, no, we have to subtract this triangle, right, from that area. So if we subtract this triangle, we will get this shaded region. Okay, so you get that, you follow that. Again, if we add this rectangle, this quarter circle, this rectangle, it will form this total area. Okay, and if we subtract this triangle, we will get this shaded region. So that's what we are going to do here, no, to solve this. Okay, so we will construct a table here. Okay, so this will be the rectangle. No, so this will be the rectangle. Its dimension is 6 centimeter and 9 centimeter. Okay, so also for the quarter circle, so this is the quarter circle. So this is 5 centimeter in radius. Also for this rectangle, so this is also a rectangle, right? So its dimension is 4 centimeter, and this side is 5 centimeter. Okay, so that will be the dimension. And also for the triangle, so this is the triangle. Okay, so this is the triangle. So we need this triangle. So for this triangle, the dimension is 9 centimeter and 7.5 centimeter. Right? So we will solve the area of these shapes, no? So this is rectangle, quarter circle, rectangle, and triangle. So for this rectangle, this is 9 times 6. So this will be 54. For this quarter circle, this will be 1/4 pi r squared. Our radius is 5. So this will be 25 pi over 4. For this rectangle, no, so this will just be base times height. So that will be 4 times 5. So that will be 20. And for this triangle, okay, this is 1/2 base times height. Okay, so this is 1/2 base times height. And we are going to subtract this. Now, if you're going to subtract this, we have to indicate a negative here. Now, so this will be 1/2 base times height. So that will be 1/2 times 9 times 7.5. So that will be 33.75. So this will be negative, just to indicate that we will subtract this area. Okay, so if we are going to sum up all this area, so again, rectangle, okay, plus quarter circle, plus this rectangle, minus this triangle, this will be the total area. Okay, so that will be 54 plus 25 pi over 4 plus 20 minus 33.75. So that will be 59.88495. Okay, now we are going to solve their respective x and y coordinate. So we will measure the x and y coordinate from the reference point. So in this case, our reference point is at this point, since the x-axis is here and the y-axis is here. So our reference point is here. So we will measure the x and y coordinate from this point. Okay, so for the x coordinate of the centroid of the rectangle, so this is the rectangle. So its centroid is here at this center, no? So its x coordinate will be this distance. So this distance is half of 6 centimeters, so that will be 3. Now for its y coordinate, so we will proceed now to the y coordinate of this rectangle. So for this rectangle, again, its centroid will be at the center. So its y coordinate, if we will analyze this, okay, so this rectangle, okay, this is 9 centimeter. Okay, so this is 9 centimeters. So the half of this, okay, so the half of this is 4.5. Okay, and we can see here that this is 5 centimeter. So this is 5 centimeter. So this is 9 centimeter. So the half of 9 centimeter is 4.5. So meaning to say, okay, if this is 5, okay, if this is 5, the half is 4.5, no? Half of 9 centimeter, 4.5, 4.5, and then 5. So the distance that we need is this distance. This distance will be 5 minus 4.5. Okay? So, 5 minus 4.5, okay, that is 0.5. So the other way around, we can also say that since this is 4, no, since this is 4, the centroid of this rectangle is here 4.5, no, so it can also be 4.5 minus 4 to solve for this distance. So this is the y coordinate, okay, of the rectangle, no, from the reference point, no, so this is 0.5. Okay, now for the quarter circle, okay, so for the quarter circle, this is our quarter circle. Okay, so if we will measure the x coordinate, so the x coordinate of the centroid will be this distance, right? So this will be this distance. So this is 6 centimeter, and this distance, what is this distance? So this distance is 4r over 3 pi. So this will be 6 plus 4r over 3 pi, wherein the radius here is 6 centimeter. So this will be 6 plus 4 times 5 over 3 pi, so that will be 8.12207. Now, for its y-coordinate, so the y-coordinate of the centroid of this quarter circle will be this distance. So this distance is 4r over 3 pi. So 4r over 3 pi, the radius is 5. Okay, so the y-coordinate will be 2.12207. Now, for the rectangle, this rectangle, okay, so the x-coordinate of this rectangle, okay, the x-coordinate of its centroid, so the centroid is here. Okay, so its x-coordinate will be this distance. Okay, so this distance is actually 6 plus half of 5. No, so this is 5. So the half of 5 is 2.5. So that will be 2.5 plus 6. Okay, so that will be the x-coordinate. 6 plus 5 halves. 5 halves is 2.5, ha, kalahati. Half of 5. Okay, so this will be 8.5. So that will be the x-coordinate. Now, for the y-coordinate of the centroid of this rectangle, okay, so its centroid again is somewhere here. Okay, so its y-coordinate is this distance. So this distance is half of 4, right? So this is 2. But since this is below, okay, the reference point, this will be negative. That's why it is negative here. Okay, so don't forget that, class. Okay, you have to consider the sign, our sign convention, ha. Since the centroid of this shape, no, of this rectangle is below the reference point, meaning to say the y-coordinate will be negative. Okay, also for the triangle, okay, so this is our triangle. Okay, so to solve for its x-coordinate, okay, so the centroid of this triangle will be somewhere here, right? It will be somewhere here. So to solve for this, for the x-coordinate, no, so this will just be from this point, no, if we are going to measure this, no, we know that um, okay, x-coordinate. So we will measure this distance, right? X-coordinate of the centroid. So this distance is actually 1/3 of this side, which is 7.5. So that will be 1/3 of 7.5. So that will be 2.5. So it is positive since it is at the right of the reference point. Okay, now for its y-coordinate. So its y-coordinate will be this point, this distance. Okay, so this distance, actually, this distance is, this is below, no? This is below the reference axis or the reference point. So this will be negative. So this distance is actually, if this distance is 3, this is 3, right? This is 1/3. This is 1/3 of 9. No, so this is 1/3 of 9. And then this is, so that will be 3. So that, and this is 4. So 4 minus 3, we can get this distance, which is the y-coordinate. So that will be 4 minus 3, so that will be 1. But since it is below the reference point, so this will be -1. Okay, so the y-coordinate is -1, okay? Okay, so here, we can now solve, no, the x and y coordinate since we already solved for the area, the x and y coordinate of each component area here. So let's apply the formula. So to solve for x bar, no? So the total area is 59.88495. So that will be times x bar, and that will be equal to ax. So area times the corresponding x coordinate. So this will be 54 times 3 plus 25 pi over 4 times 8.12207 plus 20 times 8.5. So this will be minus, since this is negative here, no? So this will be minus 33.75 times 2.5. So we can now solve for x bar. So the value of x bar will be 6.79806 centimeter. Okay, now for y bar, okay, so we are going to use our formula. Again, our total area is 59.88495, and then times y bar, so that will be equal to ay. So area times its corresponding y coordinate. So this will be 54 times 0.5 plus 25 pi times 2.12207 times 20 times negative 2 times, plus rather, plus, minus pala, minus 33.75 times negative 1. Okay, so solving for y bar, no, the answer will be 1.04228 centimeters. So this will now be the answer for x bar and y bar. Okay, so you can check that, ha. You can check your answer if it's logical. So if your x bar is 6.79806 from the reference point, so our reference point is here, so 6 point something, so it will be somewhere here, and then 1 point something, it will be, so both x bar and y bar are positive, no? So meaning to say, it is at the right side and above, no, the reference axis, no, or the reference point. So it will be somewhere here. Okay, so basically, if we draw a horizontal and vertical axis at the centroid, no, so we can, ano naman, we can say that the area above is equal to the area below, and the area at the right is equal to the area at the left, no. So basically, our answer is, ano naman, logical. Okay, so let's proceed now to the theorems of Pappus. Okay, so for this topic, we are going to apply what we have learned from our discussion in solving for centroids of composite figures or composite areas and composite lines. Okay, so we are going to apply that here. So Pappus developed two simple theorems for determining the surface area, okay, or volume generated by revolving a plane curve or a plane area about a non-intersecting axis lying in the plane. So if we are going to revolve a plane curve about a non-intersecting axis, no, it will generate a surface area. Okay, also, if we are going to revolve a plane area about a non-intersecting axis, that will generate a volume. Okay, so let's say we have here these examples, no? So let's say we have here this line, this in red ink. Now, if we are going to revolve this line, no, or this curve, now if you are going to revolve this about this axis, about the y-axis, it will produce, okay, or it will generate a cone, right? It will generate a cone. If I hope that you can imagine that if you rotate this line, okay, this line, this curve, now about the y-axis, it will produce a cone, right? So also, if you're going to revolve this line, now about the y-axis, if you will revolve that, it will produce a cylinder, right? Also for this semicircular arc, if you're going to revolve this about the y-axis, so it will produce a sphere. Okay, so there will be a generated surface area if you're going to revolve a line or a curve about a non-intersecting axis. Okay, similarly, for area, for plane area, if we are going to revolve a plane area about an axis, about a non-intersecting axis, it will generate a volume. Okay, let's say for this plane area, no, so this is a triangle. Also, if you're going to revolve this triangle, okay, about the y-axis, it will produce a cone, right? Also, for this rectangle, if we revolve this about the y-axis, it will produce a cylinder, right? Also, for this semicircle, if we revolve this about the y-axis, it will produce a sphere. Okay, so this will generate, now this will generate volume of the cone, volume of the cylinder, volume of the sphere. Okay, so it is important here, no, that we know how to solve for the centroid of the composite areas or composite lines or composite curves, because what if, no, the plane curve or plane area here are composite areas, are composite curves, no? So we need to know how to solve for that composite area and the centroid of that composite area or composite curve. Okay, so we will apply what we have learned. And also, this is also an important concept here, that we can only revolve a plane curve or plane area, no, about a non-intersecting axis. Okay, so we cannot revolve a plane curve or plane area about an axis, okay, that intersect, no, that intersect or that pass through, no, that pass through the plane curve or plane area. No, okay, so that's an important concept here, how you have to remember that. Okay, so let's talk about the formulas that we are going to use, no, for theorems of Pappus. Okay, so Pappus proposed two theorems, no? So the first theorem that Pappus proposed states that the surface area is the product of the length of the generating curve multiplied by the distance traveled by its centroid. So it is a curve, no? It is a curve, okay, that we are going to revolve here. Curve or line, okay, that we are going to revolve here. So it will generate a surface area. Okay, so the formula for this will be A is equal to Lx bar theta, or area is equal to Ly bar theta. Okay, wherein A here will be the generated surface area. The capital letter L here will be the total length, no, of the composite curve or line, no. And then X bar, this will be the centroid of the composite line, no. This will be the X coordinate, no. So also we can use this formula, no. So this will be Y coordinate. So it depends on the problem, no. It depends on the axis where we are going to revolve the composite curve, no, to know if we're going to use X bar or Y bar. Okay, so if the axis, okay, that we are going to where we are going to revolve the composite figure is at the Y axis, so what we need is X coordinate. Okay, but if the composite line or curve will be revolved, okay, about the about the x-axis, okay, what we need there will be Y bar, will be the Y coordinate. Okay, so take note of that. Now, for the Pappus second theorem, it states that the volume is the product of the area of the figure multiplied by the length of path described by the centroid of the area. So this will be the formula for the second theorem of Pappus. So this will be for volume. No, volume is equal to area times x bar times theta, or volume is equal to ay bar times theta. Okay, wherein I forgot to say, no, our theta here, okay, is the angle of revolution. Okay, so in our case, if we are going to revolve a line or a curve, a composite curve or a composite area about an axis, no, so its revolution will be 2 pi. Okay, if it's just one revolution, it will just be 2 pi. Okay, if it's just one revolution. So that will always be anaha 2 pi, our theta. Same here when you are solving for volume. So the A here, okay, is the area, the total area of the composite figure that you're going to revolve. No, so X bar here, okay, that will be the centroid, no, or the X coordinate of the centroid of the composite figure, okay, and theta here will be 2 pi, so that will be one revolution. Okay, we can also use Y bar here, so it depends on the problem. So if the composite area will be revolved about the y-axis, what we're going to use is X bar. Okay, what we need is the X bar. But if we are going to revolve the composite area about the x-axis, what we need is Y bar. Okay, so we are going to use these formulas to solve for these problems. Okay. Okay, so let's solve sample problem number 1. Compute the surface area of the cone generated by revolving the line in the figure about the y-axis. So this is the y-axis. Okay, and we have here this line. So this is line BD. no? So this line BD, okay, as mentioned in the problem, we are going to rotate this, no, about the y-axis, okay? And but the problem here is that this line BD, okay, the axis where we are going to revolve this intersect this line, right? This line. So what we're going to do here, okay, so we are going to separate, no, or divide this line BD into line BA and line AD. Okay? And then we are going to separately revolve them about the y-axis. Okay, so we cannot, ano ha, we cannot revolve this entire line BD about the y-axis because it intersects. This axis intersects line BD. So, again, what we're going to do is divide, no, this line BD into line AB and line AD, and we are going to revolve them separately about the y-axis. Okay, to solve for the surface area generated by the cone, generated, no, by revolving these two lines, no. Okay, so we are going to solve for the total area or total surface area. Okay, so to solve for the surface area generated by revolving line AB and line AD about the y-axis, we are going to separately revolve these lines. Okay, so for the area total or the total surface area, that will be the area, no, generated by revolving line AB about the y-axis, and then area 2 will be the area generated by revolving line AD, no, about the y-axis. So for line AB, no, this will be line AB. Okay, so this is line AB, and then this is 4 inches. Okay, so this is 4 inches. So we are going to solve the area generated by revolving this line, no, about the y-axis. So we are going to use the uh, first theorem of Pappus. So our formula here will be L times x bar times theta. Okay, so since we are going to revolve this line about the y-axis, so what we need here is x bar, ha. Okay, so for the total length, no, for the total length of this line, this will be 4 inches, and its x bar will be the centroid, no, will be the coordinate, x coordinate of the centroid of this line. So the centroid of this line is here, no, at the, of course, at the center of 4 inches, which is 2 inches here, no, 2 inches. So we are going to measure this horizontal distance, no. So this is the x coordinate. So this distance, this is given here, no, but if it's not given here, we have here 30 degrees, no, and this is inclined nga, no, 30 degrees, and this is 2 inches, no, this hypotenuse. So we can solve for this opposite side, no. So this is the opposite side of this triangle, so that will just be sine 30, no. Sine 30 degrees is equal to opposite over hypotenuse. So our hypotenuse here will be 4, no. So that will just be 4 times cosine 30 degrees. So 4 times cosine 30 degrees, that will be the side that we are solving. So that will be 1. No? So our theta here is 2 pi, ha? So we are going to revolve this once. Okay, so that will be 2 pi. Okay, that will be 1 revolution. Okay, so solving for A1, this will just be 4 times 1 times 2 pi. That will be 8 pi. So this will now be the area, okay, generated by revolving the first line. Now, for the second line, which is AD, so this is AD. Now, so we are going to revolve this, no, about the y-axis. Okay, so applying the formula, L times x bar times theta. Again, we will use x bar since we are going to revolve the line about the y-axis. Okay, so the length of this line is 6 inches. Okay, and our x bar here is 1.5. Okay, so this will be 1.5. So again, if this is not given, okay, so this x bar, okay, this will just be the x coordinate of the centroid of this 6 inches line, no, inclined 30 degrees here. So this will just be um, this will be at the center, no, so this will be 3. So 3 sine 30 degrees, that is 1.5. Right? 3 sine 30 degrees, that is 1.5. Okay. So times theta, our theta is 1 revolution, so that will be 2 pi. So solving for A area, or the second area, this will be 18 pi. Okay, so we just have to solve for the total area, total surface area. So that will just be 8 pi plus 18 pi. So that will be 26 pi. Okay, so don't forget to include the unit here. So we are talking about area. So the unit for area is square inches. Since this is inches, no, so the unit will be square inches. So this will now be the answer. The total surface area is 26 pi square inches. Now let's proceed to problem number 2. Compute the volume generated by rotating the area through one revolution about the y-axis. Okay, so this is the area, no? So this is the shaded area. So we are going to revolve this shaded area, no, about the y-axis. Okay, so we can do that how we can revolve this shaded area about the y-axis because the y-axis doesn't intersect, no, or doesn't pass through the uh, the uh, the area, no. So uh, here in this x-axis, no, we cannot revolve this area. Okay, because this x-axis, this passes through, no, the area. No, so we cannot revolve this area about the x-axis. So here, we are going to revolve this area, no, about the y-axis. So since we are going to revolve an area, so there will be a generated volume. No, so that's actually what we are going to solve here, the volume generated by rotating or revolving this area, no, this shaded area about the y-axis. No, so let's try to solve this. Okay, so to solve this, no, we are going to apply Pappus' second theorem. No, so we are going to use the formula. So volume, that will be equal to A times x bar times theta. So we are going to use x bar here since we are going to revolve the shaded area about the y-axis. So what we need, okay, is the x coordinate, no, of the centroid. Of the centroid of this composite figure. Okay, so we actually solved already, no, this problem, no, the centroid of this composite area in our sample problem number 7. So we already solved for the x bar. So our x bar there from our solution is 6.79806 centimeter. Okay, and our area is 59.88495 square centimeter. So we are going to just substitute that in our formula. No? So our formula is V is equal to A times x bar times theta. So our area is 59.88495 times x bar, which is 6.79806, times the theta or the revolution, which is 1 revolution, and that is 2 pi. Okay, so solving for the volume, that will be 2,557.89. So the unit for this is cubic meter, centimeter rather. So this will now be the answer for this problem. So that concludes our discussion for this topic. I hope that you learn and attain the learning outcomes. And don't forget that we have assessment tasks for this topic. You will have to submit that on our next meeting. So I hope that you are doing well. Okay, so God bless you and keep safe, class. See you again. Bye-bye.